Something in the universe is trying to get our attention, and we have no idea what it is. For decades, we've been listening to space. Radio telescopes pointed at the darkness, scanning frequencies, collecting data from objects billions of light years away. Most of what we detect makes sense. Pulsars spinning with clockwork precision, quasars powered by supermassive black holes, the cosmic microwave background, the echo of the Big Bang itself. But not everything we've detected can be explained. There are signals, emissions, patterns in the noise that don't fit our models, that appear once and vanish, that repeat with disturbing regularity, that seem to violate what we understand about natural cosmic processes. These aren't science fiction, they're real detections, recorded by our most sensitive instruments, studied by our best scientists, and they remain unexplained. What I'm about to share with you are genuine mysteries, signals from the depths of space that challenge our understanding of what's possible. And I promise you this, the final signal we'll discuss is the one that keeps astronomers awake at night. Because it suggests that space isn't just noisy, it suggests that something out there is active, persistent, and completely indifferent to whether we're listening. Let's begin.
On August 15, 1977, a radio telescope in Ohio detected something that shouldn't have been there. The signal lasted exactly 72 seconds. It was strong, incredibly strong, 30 times more powerful than the background noise, and it came from a very specific direction in space, near the constellation Sagittarius. The astronomer monitoring the data was so shocked by what he saw that he circled the printout and wrote a single word in red pen: "Wow." The signal has never been detected again. Here's what makes it disturbing. The frequency was 1420 megahertz. That's the hydrogen line, the most common element in the universe. It's also a frequency that many scientists believe would be an obvious choice for any intelligent civilization trying to communicate across interstellar distances. Natural sources can produce emissions at this frequency, comets, clouds of hydrogen gas, but they produce broad-spectrum noise, not the narrow-band signal that was detected. The wow signal was focused, precise, almost laser-like in its specificity. For decades, scientists tried to find a natural explanation, a comet passing through the telescope's field of view, a reflection from Earth-based sources, a glitch in the equipment. But nothing quite fits. The signal came from deep space. It was too strong to be terrestrial interference, and it never repeated, which rules out most natural periodic sources like pulsars. 47 years later, we still don't know what caused it. It could have been a random natural phenomenon we've never observed before or since, a cosmic fluke, or it could have been something else entirely. Either way, it was a signal from the void that arrived once, announced itself, and then vanished into silence. But this was only the beginning.
In 2007, astronomers discovered something new, something that shouldn't exist according to any model we had. Fast radio bursts, FRBs. These are intense pulses of radio waves lasting just milliseconds, releasing as much energy in that brief flash as our sun produces in an entire day. They come from billions of light years away, from galaxies so distant we can barely resolve them. The first one was discovered buried in old data from 2001, detected by the Parkes Observatory in Australia. It was designated FRB 010724, a single burst, no repetition, no follow-up signals. And then we found more. Dozens of them, hundreds, each one a brief, violent emission of radio energy with no obvious source, no visible object, no counterpart in other wavelengths.
What makes FRBs deeply unsettling is their power. To produce that much energy in milliseconds requires extreme conditions. Colliding neutron stars, magnetar eruptions, perhaps evaporating black holes, or phenomena we haven't even theorized yet. But here's where it gets stranger. Most FRBs happen once and never repeat. A single burst from a random point in the universe, and then silence forever. Except for some that do repeat. In 2012, astronomers detected FRB 121102, and unlike the others, this one came back again and again, hundreds of times over the following years, always from the same location, a dwarf galaxy 3 billion light-years away. The repetition changed everything, because now we could study it, track it, try to understand it. And what we found was even more disturbing. The bursts weren't random. They showed patterns, periodicities, windows of activity, followed by silence. The source would emit dozens of bursts over a few days, then go quiet for months. It was behaving almost like it had a schedule. Scientists proposed explanations: a young neutron star orbiting a companion, magnetic field interactions, precession of a magnetar's rotation axis, creating periodic visibility. But none of the models perfectly fit the data. And then we discovered something that made it worse. Some of the repeating FRBs showed what's called downward frequency drift. The burst would start at a high frequency and slide down to a lower frequency over the course of milliseconds, like a descending whistle. This kind of behavior is seen in pulsar emissions, but FRBs are thousands of times more energetic than any pulsar emission we've ever detected. Whatever is producing these signals is unlike anything we've ever observed, and they're coming from all across the universe, from every direction, at a rate of thousands per day across the entire sky. Most of them we'll never detect. They're too far away, too brief, too faint. But the ones we do catch are screaming at us across billions of light-years of space, and we don't know why.
Not all unexplained signals come from space. Some of them turn out to be embarrassingly terrestrial. For years, the Parkes Observatory in Australia detected strange signals called peritons. They looked almost like fast radio bursts, brief, intense, but something about them was wrong. They appeared too frequently, and they showed up across multiple telescopes simultaneously, which suggested a local source rather than a distant cosmic origin. Scientists were baffled. The signals had all the characteristics of deep space emissions, but the pattern of detection didn't make sense. And then, in 2015, they figured it out. Someone had been opening the microwave oven in the observatory's break room while it was still running. The microwave door, when opened prematurely, released a brief pulse of electromagnetic radiation at exactly the right frequency to trigger the radio telescope's detection systems. Mystery solved, embarrassment acknowledged. But here's why this matters. The periton signals reminded scientists of something important. Not every anomaly is cosmic. Sometimes the universe isn't sending us strange signals. Sometimes we're just detecting our own noise. Which raises an uncomfortable question. How many of the unexplained signals we've detected are actually natural cosmic phenomena, and how many are artifacts, glitches, or terrestrial interference we haven't identified yet? The RAW signal came from a telescope that was later decommissioned. We can't go back and verify it with modern equipment. Some FRBs have been detected by only one telescope. No confirmation. No follow-up. We trust our instruments, we trust our analysis, but we've been wrong before. And that uncertainty, that nagging doubt, makes every unexplained detection both more exciting and more frustrating. Because we might be listening to something profound,
Or we might be listening to cosmic static and seeing patterns where none exist. What came next was far harder to ignore.
In 2019, the Parkes Observatory detected something unusual. A narrow-band radio signal at 982 megahertz, apparently coming from the direction of Proxima Centauri, the closest star system to Earth. The signal was designated BLC1, Breakthrough Listen Candidate 1. What made it interesting was its characteristics. It was narrow-band, meaning it occupied a very specific frequency rather than being spread across a range. Natural sources tend to produce broad-spectrum emissions. Narrowband signals are more commonly associated with artificial transmitters. The signal appeared multiple times over several observation sessions, always from the same direction, always at roughly the same frequency. And Proxima Centauri, 4.2 light-years away, is known to have at least 2 planets. One of them, Proxima Centauri b, orbits in the star's habitable zone. For a brief moment, the signal generated intense interest. Could this be a transmission from a technological civilization on a planet in our nearest neighboring star system? Researchers analyzed the data carefully. They looked for frequency drift that would indicate a source moving relative to Earth. They searched for patterns in the signal's modulation. They compared it against known sources of interference. And gradually, the signal's origin became clearer. It wasn't from Proxima Centauri, it was from Earth. The frequency, the timing, the characteristics, all of them matched human-made transmissions, likely from a satellite or ground-based source that hadn't been properly cataloged. Another false alarm, another reminder that space is full of human noise. But what disturbs scientists about signals like BLC1 isn't that they turn out to be terrestrial, it's how difficult it is to rule out cosmic origins. It took months of analysis, multiple observation sessions, and cross-referencing against databases of known interference sources to definitively identify BLC1 as human-made. Which means if a genuine signal from another civilization ever reaches us, buried in the noise of our own transmissions, it might take years to recognize it, or we might dismiss it entirely. We're listening, but we're listening through layers of our own static. And somewhere in that static, something real might be hiding.
Magnetars are neutron stars with magnetic fields a quadrillion times stronger than Earth's. They're the most magnetic objects in the known universe. And occasionally, they scream. Magnetar flares are among the most energetic events we've ever detected. In December 2004, a magnetar called SGR 180620, located 50,000 light-years away, released a flare so powerful it temporarily disrupted Earth's ionosphere from 50,000 light-years away. If that flare had occurred within 10 light-years of Earth, it would have caused a mass extinction event. But here's what's strange about magnetars. We don't fully understand them. The magnetic fields are so intense they violate our normal models of how matter behaves. Space itself becomes polarized. Atoms stretch into cigar shapes. Light slows down in vacuum because the magnetic field creates virtual particle pairs that interfere with photon propagation. And the signals they produce are bizarre. Some magnetars emit regular pulses, like pulsars, but others produce erratic bursts, signals that appear without warning, last for seconds or minutes, and then vanish. One magnetar, SGR 1935+2154, produced a fast radio burst in 2020, the first FRB ever detected from within our own galaxy. This discovery confirmed that at least some FRBs originate from magnetars, but it didn't explain all of them. Because SGR 1935+2154's burst was relatively weak, If FRBs we detect from distant galaxies are all magnetar flares, they must be thousands of times more powerful than anything we've observed from magnetars in the Milky Way, which suggests either distant magnetars are far more energetic than ours, or something else is producing those signals. And here's the unsettling part. Magnetars shouldn't exist in the first place. The magnetic fields are so strong they should tear the star apart. The stress on the crust should cause it to crack and collapse. But they persist, emitting signals we can detect across the galaxy and beyond, behaving in ways we can't fully predict. They're natural objects, we know that, but they exist at the edge of what physics allows. And when we listen to them, we're hearing something that shouldn't be stable, something that's constantly on the verge of catastrophic collapse, a signal from the edge of possibility itself.
When you point a radio telescope at empty space, you don't get silence, you get noise, a constant background hiss from every direction. Most of this noise is expected: the cosmic microwave background, emissions from distant galaxies, thermal radiation from gas clouds. But in 2009, a team of scientists analyzing data from radio surveys noticed something odd. There was excess radio emission, more signal than could be accounted for by known sources. They called it the radio background anomaly. The signal was faint, spread across the entire sky, no obvious point of origin, just a diffuse glow of radio energy that seemed to come from everywhere at once. Scientists proposed explanations. Maybe it was from the first stars that formed in the early universe. Maybe it was from black holes in distant galaxies. Maybe it was dark matter annihilating and producing photons. But none of the models quite worked. The excess was too strong to be explained by early stars alone, too evenly distributed to be from localized sources like black holes, and the spectrum didn't match predictions for dark matter annihilation. More data was collected, more surveys conducted, and the anomaly persisted. What makes this signal disturbing isn't its intensity. It's faint, barely above the noise floor. What's disturbing is that it's everywhere. It suggests that space itself, the background fabric of the universe, is producing more radio emission than we expect. That there's some process, some mechanism operating on cosmic scales that we haven't accounted for. Or it could be something simpler: terrestrial interference we haven't identified, calibration errors in our instruments, a systematic issue that affects every telescope the same way. But if it's real, if there genuinely is excess radio emission filling the universe, then we're missing something fundamental about how the cosmos works. We're detecting a signal from the structure of reality itself, and we can't explain it.
In 2020, astronomers detected a new repeating fast radio burst, FRB 2020-1124A. It behaved like other repeating FRBs, bursts of radio energy, milliseconds long, incredibly powerful, always from the same location in a distant galaxy. But this one did something different. The bursts showed extreme variability. Some were incredibly bright, others were faint. The intervals between bursts ranged from seconds to hours. There was no clear pattern, no periodicity. And then scientists noticed something in the data that made them pause. Some of the bursts showed polarization changes. The orientation of the radio waves was rotating, twisting, as if the signal was passing through a magnetized environment. This suggested the source was embedded in a complex magnetic field, maybe near a magnetar, maybe in a supernova remnant, maybe in some exotic environment we haven't identified yet. But here's what was truly strange. The polarization changes weren't random. They showed structure, organization, like the signal was interacting with something along its path to us. And then, over the course of several months of observation, the bursts just stopped. FRB 2020-1124A went silent. As of now,
it hasn't been detected again. Scientists don't know if it will come back. They don't know why it stopped. They don't know what causes the polarization changes or the extreme variability in brightness. It's as if something 3 billion light-years away turned on, sent us hundreds of signals over a few months, and then turned off. No explanation, no follow-up, just silence. And this is where the scientific process becomes uncomfortable, because we can propose models, we can write papers, we can suggest magnetars and neutron star collisions and exotic astrophysical processes, but we can't test them, we can't reproduce the signal, we can't visit the source. All we can do is watch and wait and hope it happens again. And in the meantime, we're left with data that doesn't quite fit any theory, with signals that seem to obey rules we don't understand. We're listening to the universe speak, but we don't know the language.
Let me tell you about the signal that disturbs scientists the most. FRB 121102, the first repeating fast radio burst ever discovered. For years after its discovery, it seemed random. Bursts appearing unpredictably, sometimes dozens in a day, sometimes none for months. But in 2020, after years of continuous observation, scientists noticed something. The bursts weren't random, they followed a pattern. For 4 days, the source would be active, emitting bursts at irregular intervals, and then it would go silent for 12 days, exactly 12 days, and then it would turn on again for 4 days. A 16-day cycle, repeating with disturbing precision. This changes everything, because natural astrophysical processes don't usually follow precise schedules. Pulsars spin at constant rates, yes, but their emissions are continuous. Magnetar flares are chaotic. Supernova remnants evolve on timescales of centuries. But FRB 121102 has a calendar, an on-off switch that operates on a predictable cycle. Scientists proposed explanations. Maybe the neutron star is orbiting a companion, and the companion blocks the signal for 12 days out of every 16. Maybe the neutron star's magnetic field precesses, and we only see the bursts when the field is oriented toward us. Both models could work, mathematically, but neither has been confirmed. And here's what keeps astronomers awake at night. If FRB 121102 operates on a 16-day cycle, how many other repeating FRBs have cycles we haven't detected yet? How many of them are sending signals on schedules we'll never notice because we're not watching long enough? And, more disturbingly, what if the cycle isn't natural? I'm not suggesting intelligence. I'm not invoking anything beyond physics. But I am saying this. We've discovered a signal from 3 billion light-years away that operates on a precise, repeating schedule. It turns on, it turns off, it turns on again. And we don't know why. It could be orbital mechanics. It could be magnetic precession. It could be a process we haven't even theorized yet. But it's regular, predictable, structured. And that structure implies something. Organization, a mechanism that operates with clockwork precision across timescales of billions of years. FRB 121102 isn't just a signal. It's a reminder that the universe contains processes we barely understand, objects that behave according to rules we're only beginning to glimpse. And it's out there, right now, 3 billion light-years away, turning on and turning off every 16 days, sending bursts of energy across the cosmos, for no reason we can confirm.
We've listened to signals from across the universe. Some turned out to be microwave ovens. Some are neutron stars behaving strangely. Some are bursts of energy from sources we can't identify. And all of them remind us of the same uncomfortable truth. Space is not silent. It's full of signals, emissions, patterns and noise and bursts of energy that propagate across billions of light years. Most of it we understand. Pulsars, quasars, supernova remnants, the echo of the Big Bang. But not all of it. There are signals we can't explain, patterns we can't predict, sources that turn on, send us a message, and then vanish into silence. And here's what we're left with. Either these are natural phenomena operating according to physical laws we don't yet fully understand, exotic astrophysical processes at the edge of what's possible, magnetars and colliding neutron stars and black hole interactions producing signals we're only beginning to detect, or we're missing something fundamental about how the universe communicates information, about what kinds of processes can produce organized, structured emissions. We built radio telescopes to listen. We pointed them at the sky, expecting cosmic silence, punctuated by occasional stellar noise. What we found instead was a universe that never stops broadcasting. Signals from every direction, some random, some patterned, some repeating with clockwork precision. And most of them we'll never understand, because we're listening with instruments designed to detect what we expect. We're analyzing data using models based on what we already know. But the universe doesn't care what we expect. It doesn't care what our models predict. It just keeps sending signals from the depths of space, from billions of years in the past, from places so distant the light will never reach us. And we're here, on a small planet, listening, trying to make sense of transmissions we were never meant to receive. The WOW signal arrived once and never came back. Fast radio bursts flash across the cosmos thousands of times per day. Magnetars scream with magnetic fields that shouldn't exist. And FRB 121102 turns on and off every 16 days with no confirmed explanation. We don't know what it all means. We don't know if it means anything. But we know this: the universe is active. It's noisy. It's full of signals we're only beginning to detect. And it has been broadcasting long before we existed. And it will continue broadcasting long after we're gone, completely indifferent to whether anyone is listening.